A'udhu billahi minash shaitani rajim. Bismillahir rahmanir rahim. In this unit, we will study free space path loss model for wireless communication system. As you know that free space path loss model is used to predict received power when the transmitted and receiver have clear unobstructed line of sight between of them. For example, satellite communication and microwave line of sight between these transmitter and receiver because they usually undergo free space propagation. In this unit, we will discuss firstly we discuss path space loss model, then we discuss about power density in free space, then we discuss about effective isotropic radiated power, and we discuss the relation between gain and effective area of antenna, and then we discuss about free space model, and then we discuss about free space model in logarithmic scale. And finally, we discuss about Friss model with gain and then Friss model with log scale. For any type of wireless communication system, the signal inherently disperses with distance. Therefore, an antenna with a fixed area can receive less signal power when it moves further it is from the transmitting antenna. For satellite communication, this is the primary model for signal loss. And even if no other source of attenuation or impairment are assumed, a transmitted power, yeah, signal power attenuates over distance because the signal is being spread out over a larger and larger area. This form of attenuation is known as a free space loss, which can be expressed in terms of ratio of radiated power to the power received by the antenna. And generally, it is expressed in decibels, which is just by taking 10 times of the log of the ratio. An isotropic is an idealized antenna that radiates and receives electromagnetic wave uniformly in all directions. In other words, it has a equal radiation and reception pattern in all directions with no preferential radiation or reception in any particular direction. The power transmitted per unit area can be defined as power density in free space and can be written as power density is equal to power divided by 4 pi d square, where Pt is power transmitted and other word radiated by the source, and d is the distance from the source, where the factor pi 4 pi d square in the denominator account for the spreading of the wave over an expanding spherical surface as it propagates through the space. As the distance from the source increases, the same total power is distributed over a large area and resulting in decrease in power density. It is important to note that this formula assumes ideal condition of free space with no obstacle, no reflection, or even any other effect that could affect the propagation of electromagnetic wave in space. In practical scenario, power density can be influenced by many factors such as obstruction, multipath propagation, absorption, scattering, and many other electromagnetic parameters which can cause additional attenuation and variation in the power distribution. Effective isotropic radiated power is a fundamental parameter in wireless communication system that characterizes the power density of a radio signal in a specific direction. EIRP takes into account the gain of the transmitter antenna and the loss in the transmission medium to determine the effective power radiated by the antenna. EIRP is expressed in units of power, usually in watts, and generally it is represented in decibels, 1 watt, a decibel watt. It represents the equivalent power that an isotropic antenna could need to emit to achieve the same power density in a particular direction as the actual antenna. Mathematically, ERP can be calculated by multiplying the power supplied by antenna, transmitted power, as by the antenna gain. So we can write that EIRP is equal to transmitted power multiplied by the antenna gain, transmitted power PT and antenna gain GT. So EIRP is equal to PT multiplied by GT. The transmitted power is a power delivered to the antenna input, while the antenna gain represents how effectively the antenna radiates power in a specific direction compared to the isotropic radiator. The effective antenna aperture or area is a theoretical value which is measure how effective an antenna is at receiving power. The effective aperture or area can be calculated by knowing the gain of receiving antenna. It can be defined gain is equal to 4 pi AE divided by lambda square, where G is the gain, A is the effective area or effective aperture, and lambda is the wavelength. As we know that lambda can be defined as C over F, where C is the speed of light, 3 to 10 power 8 meter per second, and F is the frequency of the antenna. So gain can be written as C pi F square C square AE. This equation clearly shows that gain is directly proportional to the effective area, and gain is also directly proportional to the square of frequency. And C is a constant, so gain is a direct function of F and AE. In wireless communication, loss is generally written as ratio of transmitted to the received power. Therefore, for an ideal isotropic antenna, free space loss can be defined as Pt over Pr is equal to 4 pi d square over lambda square, and which, as you know that lambda can be defined C over F. So Pt over Pr can be written as 4 pi Fd bracket square divided by C square, where Pt is the signal power at transmitting antenna, Pr signal power observed at the receiving antenna, and lambda is a carrier wavelength, and F is a carrier frequency. D is the propagation distance between transmitter and receiver. C is a universal constant, speed of light, which is 3 to 10 power 8 meter per second. Here, D and lambda are observed in the same unit as meter. Free space loss generally also expressed in logarithmic scale, and for logarithmic scale we take the logarithmic ratio of Pt over Pr and multiplied by 10. As from the previous slide we see that Pt over Pr is equal to 4 pi d over lambda square. So log power 2 becomes the multiple of the 2. So it becomes 20 log 4 pi d over lambda. And we use the further logarithmic properties. We can write minus 20 log lambda plus 20 log d, and 4 pi is a constant, so their log and multiply by 20, it makes 21.98, and in the form of decibels. And finally, we can convert our equation in terms of frequency. So we can write loss is a 20 log f plus 20 log d minus 147.56 decibel. Fritz's model is further improvement of free space path loss model. In this model, we take into account the gain of both transmitter and receiver antennas gain, which can yield the following free space loss equation. Can be written as Pt over Pr is equal to 4 pi square d square divided by Gt Gr lambda square, where Gt transmitter antenna gain, Gr receiver antenna gain, lambda wavelength, carrier frequency wavelength, and d is the distance between transmitter and receiver. We can further simplify G in terms of effective area, effective aperture. As you know that effective area of the transmitter can be written as Gt lambda divided by 4 pi. When we incorporate this equation to the Frisbee equation, our equation becomes pi d bracket square divided by AR, yani receiver aperture, या receiver effective area, and AT, transmitter effective area, and lambda is equal to, can be converted as a C over F, where C is the speed of light and F is the carrier frequency. So our free space model equation can be written as CD bracket square divided by F square divided by AR divided by AT. Fritz's free space model in logarithmic scale can be written as LdB is equal to 20 log lambda plus 20 log d minus 10 log ATAR, and similarly, which further simplified in terms of frequency is equal to minus 20 log f plus 20 log d minus 10 log ATAR plus 169.54 decibels. But at the same time, same antenna dimension and separation, the longer the carrier wavelength, lower the carrier frequency, the higher is the free space path loss. It is interesting to compare equation, free space model equation with Friis equation. The free space equation indicates that as the frequency increase, the free space loss also increase, which would suggest that at higher frequency, losses become more burdensome, which is not true. However, the equation, Frisbee equation, shows that we can easily compensate for this increased loss with antenna gain. In fact, there is a net gain at higher frequency. Other factors are remaining constant. So in other words, Friis-free equation is a little advancement as compared to the free space model to design and model the wireless communication system. Thank you.